welcome back to my math teaching today. Um, Today is the second day of the new year 2021, and we went through a very difficult times, very challenging year of 2020. So before I get into the lesson, I would like to share some of my thankful to all our doctor and nurses and the healthcare worker who have brought the great contribution and success for the vaccination. And we're looking forward to the better year of 2021. So best wishes to all of you, my audience. So now let me get right into the lesson today. So in the lesson today, I would like to talk about the area under the curve, which is the new unit of my second calculus course that maybe in a few weeks, I will be able to finish and publish it. So the topics today is the area under the curve. As you can see on the board, I have two diagrams I'm going to show you. So let's take a look at the first diagram. So on the first diagram here, I draw a function and I call this function is f of x function. Then underneath this function, I draw a region and I shaped it. This region represents the area of the region underneath the function. And I represent this area by the name A, stand for area of the function of x. So A of x. Now I would like to explain why do we name this area A of x. The reason because if you notice, this area lie under the curve and shaped it by the curve wherever the curve go. So this area is not a fixed area. It's not a fixed area. So if I mark from year 0 to here is a unit. I call it A, it could be A here could be 1 or 2 unit. And I mark this unit here on the axis is B, I call it B, but it could be 5 or 6, whatever unit, right? We don't know. I just name it A and B. So I move the area, I mark the area between A and B, the region between A and B, with the dot, the first dotted line here. As I move this first dotted line to the second dotted line here, and let's say I move an x unit, I move from B to x unit, and I call it x unit because I don't want to have a fixed like 1 or 2 or 3 units. So I just say, let's say I move from B to an x unit here. Then my area will extend it from here on the way to here, right? So that's my area getting bigger by the unit of x. So as long as I keep moving to the right hand side, and let's say this curve is keep moving, then this area will be shaped under the curve, and also will be extended as well as I move to the right? Because this function is keep growing. It not stop right here. So that's why we know that this area is not a fixed area, and this area is keep changing, and we call the rate of change, right? In calculus, this area keep changing from unit A to B, from A to X, and maybe from A to 10 unit or 20 unit or whatever I want to move it, right? And I named this area is the area under the curve, shaded by this region, and this area is a function of x. So that's my first diagram, okay? Now, Let's say in the second diagram, I start getting into how to calculate the area under the function f of x. To make it simple, because usually we always try to make the lesson from simple to complex. So to make it simple, instead of drawing a curve like the first on the top, I'm going to draw just the linear. So my function now is the linear function. So this linear function f of x here is a straight line. And this straight line have an equation y equal to x plus 1, which is any formula of the linear function is always y equal mx plus b, where m here is 2, which is the slope of the linear, right? And y here is the y-intercept. So you can see that this linear function go through the y-intercept at 1 right here. I marked right here. And therefore, this number 1 stands for this, right? If you only learn up to this level, you only went through math 9, math 10, math 11, you know I'm talking about the linear function, right? The linear function have a standard form y equal mx plus b, where the b value here is 1, which is the y-intercept here. Okay, so that is how I introduce to you this, the linear function and the equation of it. Now, underneath this linear, I draw the area under this, and I shade this area, and I call this area is A of x as well. And I mark from here 0 to 1, and then from 1 to x. And I draw this trapezoid. This shape is the shape of trapezoid. So I call this area is the area of trapezoid. Area A stands for area, or just say area of trapezoid, and I name this trapezoid is PQSR. PQSR. So how do we find the area of this trapezoid? The question is, how do we find? Now, first, we have to apply the formula of calculating the area of the trapezoid. And due to the geometric shape here of trapezoid, the formula to find the area of trapezoid will be equal the length, the short length here, right? RP, adding with the longer length SQ, divide by 2 to take the average, multiply with the height of the trapezoid. And the height of the trapezoid turned out to be from 1 to x here. That is the height. That's why I marked the 90-degree angle here, represent for the height of the trapezoid. So now the area of this trapezoid will be equal, I'm going to write the formula down here, will be RP, which is the length RP, adding with the length SQ, divide by 2, and multiply, or put in the bracket, time with the height. Okay, time with the height. And the height here turned out to be this unit. And how do we find this unit? X minus 1. So if x here is 4, then 4 minus 1 is 3. The length here is 3. If x is 5, then 5 minus 1, the length here is 4. So we just say x minus 1. X minus 1. This represents the height of the trapezoid. So I mark the height on the top. Okay, so this is the formula to find the area of the trapezoid. Now, let's examine how do we find the length RP here, right? So area equal RP, but how do we find RP? Now, if this x is 1, right, and let's say the y coordinate of the p, any coordinate have the coordinate x and y, right? So we know x coordinate of the p here is 1. What about the y? And let's say this is con y1, okay, right here. Let's calculate y1. It turned out y1 is the length of PR, right? Y1 is the length of PR, Y1 unit, right? From 0 to Y1 is the length of PR. And how do we find Y1? Because we know this linear function have a function y equal to x plus 1. So if we substitute x equal 1 into this function, then we'll be able to find the y coordinate y1 of this x1, right? So let's just talk about the PR first, or RP, right? So RP will be equal to times x, and x is just 1, adding with 1 equal 3. So now we know the y1 here equal 3. So the length of RP equal 3 unit, right? Now we calculate, we know. What about the length of SQ? Let's find out. The length of SQ will be equal x, right? And we substitute in function, which is just the same like 2x plus 1. So the length of this turn out, because we name this is the x unit, we substitute in here in the function, it's just the function itself. So this is y1 and this is y2. y2 equal this. This is the unit of y2, which is y2 here, right? On the way from here, of this. So this is y2 is a unit of SQ, and unit of SQ, because we mark this is x unit, we substitute in here just the function itself. So this is SQ. So now we know that the area under the curve is the area of the function. So let's establish the area of this function. So I'm going to say area of x, of function x equal, follow this formula, RP, which is 3, right? RP is 3, adding with SQ is 2x plus 1, and all of this divided by 2, times with the height, and the height is x minus 1. X minus 1. So let's simplify this function for now, okay? So I'm going to distribute this first bracket to the second bracket, right? I'm going to distribute it to simplify it. I'm going to multiply, okay? So x times 3 is 3x. X times 2x is plus 2x squared. X times 1 is plus x. So I'm done with x. Now I go to minus 1, right? Distributed 2. So minus 1 times with 3 is minus 3. Minus 1 times 2x is minus 2x. Minus 1 times 1 is minus 1. All of this will divide it by 2. So simplify again. What do I get? I have 2x squared divided by 2. Okay, maybe just simplify the top first, okay? So I have 2x squared, 3x plus x is 4x. 4x minus 2x is plus 2x. And minus 3 minus 1 is minus 4. All of this divided by 2. So that's my function. Let's simplify one more. So we have this is divided by 2 time with this. Okay. So simplify this. I have x squared, right? Because 2 divided by 2 is 1. So 1x squared plus 2x divided by 2 is just x. Minus 4 divided by 2 is minus 2. So this is the function of this area, right? And whatever x is, we substitute in there, we will figure out what is the numerical value of this area, okay? So this is the function area. And let's say I mark this function is f of x, big f of x, okay? So this function is x squared plus x minus 2. This is function of the area, the same like a of x. So I just call it f of x, but big f of x, but that's a function, right? Okay. So now based on this diagram, we develop the area under the curve of this linear function. What I want to show you, because we know that this area is changing, right? If we move the x unit along the axis here, then the area is not fixed. It's gonna get bigger and bigger under the linear function, right? So we know that this area is actually just the rate of change function, right? So let's say if I take the rate of change of this area, let's say ax, I take the rate of change of it. So what does it look like? I take the rate of change. 2 times 1, right? This is 1, is 2, x. X here becomes plus 1, and this becomes 0 when I take the rate of change. Now, if you look back to the original function, the linear function, does this look like? Yes, it looked like, right? So it turned out the rate of change of this area, which is the derivative of the linear function, actually not the linear function, the derivative of the area function turned out to be the linear, to be the function 2x plus 1, which is equal the y function, okay? Or equal the original f of x function. So you see that the derivative of this area function turn out to be the curve, turn out to be the linear function, turn out to be the function. So the derivative of the area function is the function itself. The derivative of the area function is the function itself, which is whatever the function is. In this case, it's a linear function. In this case, the derivative of this area will be this curve. So that is the purpose of the lesson today I would like to introduce to all of you. Now, let me show you, so what if we do the antiderivative of this function? So let's do antiderivative. So if we integrate this function to x plus 1 or antiderivative, right? And we integrate this from 1 to x. Let's say from 1 to x. Let's do the integration of this on, of course, the dx. So that will become 2 divided by 3, right? Because, no, 2 divided by 2, x squared plus x plus c. So we simplify this, it will become x squared plus x. And if we want to find c, we substitute whatever in here. So let's take a look at this. So if we do antiderivative, we get x squared plus x, which is this function. And our c in this k is minus 2. This c here is minus 2, right? So if we do the antiderivative, we get back to the fx function, or we get back to the area function, which is x squared plus x plus c, and in this case, our c is minus 2. So now you will see the three things we mentioned today in this lesson. To find the area under the curve of the function, right? We establish the area function. And we realize that the rate of change of our area function turned out to be the function itself. So if I take derivative area a prime of x, I got back to the function f of x. So the derivative of the area, the rate of change of the area under the curve is a function itself. Antiderivative of this area function, we get back to the original function of the area. So in order to find any area under the curve, we do the integration of that function, and we mark the region we want to integrate from 1 to x or from a to b. So that's the basic idea of the relating between the area under the curve and its function and its derivative, and connect it to all the lesson we have learned so far, right? So far you have learned with me about the integration of the using the substitution, integration using partial and fraction, integration using substitution of u. That is just for your calculation, computation, to find the integration, to find the numerical value of integration. But now get into the concept, you understand that to find the area under the curve function, right? To find the function, original function, we take the derivative of the area function under the curve. So the derivative of the area function under the curve is the curve itself. And to find the area under the curve, we have to do antiderivative of that function so that we get the function area. So now from function area, if we want to integrate the area from unit 1 to unit x, or we want to integrate from unit A to unit B, all what we have to do is take the integration of the function given like this, and we will, in this case, if we want to find the area, you will substitute here is 1 and here is x, and multiply out something like that, which is we have learned in the past. So that's how I introduce to you the lesson today of area under the curve. Now, the next video, I will get right into the find out the region under the curve of the area. So stay tuned for that. We'll have a lot more interesting lesson to learn today. So I hope that this lesson very clear to you, and you will understand the concept of what is the area under the curve, how to get back to the original function, how to find the derivative to get to the function of the original function. So thank you for watching, and stay tuned for our next lesson. I will get right into the lesson of it. And to find the area under the curve, we have we can use a derivative like this or antiderivative like this, which is very easy, right? We can just follow the rules and the rules how to find the integrate the area and find it. But also, I have in this unit, I have introduced to you about the sigma notation and the sum of the natural, because we have another way of finding the area under the curve um, that related to the sigma notation. So that will be come to the next lesson. So thank you for watching my video today. Bye for now and stay tuned for the next video.